Hello everyone, I'm Rongyang, a postdoc from the Center for Computational Science and Center for Quantum Computing. First, I would like to thank the authors of this workshop provide the opportunity to let me discuss quantum simulation on current nowadays quantum computer. And also, I present this talk on behalf of our group leader in Sensei who cannot attend this workshop. And our main collaborators are Xiaohao and Zhiki also from our group. And so the first part, I will briefly introduce the quantum simulation and also quantum computer. And here I will emphasize that currently we are in the so-called knowledge intermediate field quantum area. So we only have knowledge disco device. And then I will introduce the algorithms in this area, which is operational quantum algorithm and as efficient system. So that's this to simulate quantum many-body system, we call it the operational quantum micro server. And it's a very promising algorithm, but I will show there are a lot of issues and challenges in VQE. And although that current quantum computing has a lot of problems and challenges, we still try to use NISCO device combined with the VQE to try to make some applications to simulate a correlated quantum many-body system. I will show several works from our group. Finally, I will close the talk with a summary. And so the system we have interest are these quantum many-body systems. We know that one of the basic properties of this quantum many-body system is that when you increase the system size, the degrees of freedom will increase exponentially, which means if you want to simulate it on classical computer, it will require exponentially large resources. But we can also think about this question in other way that like Richard Feynman said that if you want to simulate the nature, I think he means a nature of quantum system with matter make it quantum mechanical, which means we can make your simulation itself quantum mechanically, which means you can use the other quantum system. Currently, we know that they are quantum computer and a quantum simulator to simulate your system of interest. So the quantum simulation means simulating a quantum system by using the other quantum systems, i.e. some highly controllable quantum devices. And so currently the mainly used quantum computer, which called circuit-based quantum computer, and it can be simulated use quantum circuit model. And so in the quantum computer, we have a quantum state, and this state formed by qubits, and each of qubits are two-level quantum mechanical system with the state 0 and 1. And then we have a quantum logic gate, which can operate the qubit and to update the quantum state in the quantum computer. And this logic gate is basically a quantum circuit operating on a small number of qubits. For example, if you operate 1 qubit, it's called 1 qubit gate. And if you operate 2 qubits, it's called 2 qubit gate. And after you apply a series of quantum gate to your qubits, in the quantum computer, you can form a very complicated, highly entangled quantum many-body state, and that state include the solution of your problem. So you need to measure the information, and that's some classical bit strings from this quantum state. And so here I focus on this how to solve the quantum many-body problem by quantum computing. In principle, we can use the quantum adiabatic process. So our goal is to find the ground state of some Hamiltonian of interest here, HF. And so we can starting from a very simple Hamiltonian HI and with the known ground state. And this ground state can be created by applying a simple unitary operation on the vacuum. In quantum computer, vacuum is the nothing but 0, state. And so in quantum computer, you can prepare this initial state easily, and then you can construct some mixture Hamiltonian, which is a time-dependent Hamiltonian. And at the time equals to 0, it equals to this initial Hamiltonian HI, and at time equals to the big T, it will go to the Hamiltonian HF. And so based on this time dependent Hamiltonian, you can create the time evolution operator. And you can use this time evolution operator, which is a unitary operator, to operate the initial state of psi I, and finally you get the state of psi big T. And based on the quantum adiabatic theorem, that for sufficiently long time, you can get a state very close or equals to the ground state of the Hamiltonian HF. And on quantum computer, you can also realize such a very complicated unitary operator and update your initial state. And finally, in your quantum computer, you can create the ground state of the Hamiltonian of interest. And then you can measure it and get the information and announce that you solve this Hamiltonian, which means if you have a fault-tolerant quantum computer, it's equivalent to say that you can solve the quantum many-body problem. But currently, we have there exists some fatal weakness to block this approach. This is that long-time evolution on current accessible quantum devices is impossible. Why? Because we are in the NISQ area. That's currently our quantum computer has noise. So we don't have a perfect quantum computer. What we have only is the noisy quantum devices. And on such device, what we can do is we can have only tens to hundreds qubits without error correction. And also, we can only perform several or tens depth circuit evolution on these noise devices. For example, a typical example of this NISQ device is Google's Sigma quantum computer, since it can perform a quantum circuit include 53 qubits with 40 depths. But in comparison, that if you want to construct the time evolution operator, I mentioned before that for one dimension you need about 20 depths circuit, but for 2 dimensions you need around 40 depths. Even for the time period is very small. So which means the quantum adiabatic evolution is hopeless in NISQ area. So to use these noisy quantum devices, we need to develop a special algorithm. And the key point is only the shallow depth of circuit can be considered. So the near-term aim of quantum computing is achieving useful quantum advantage on NISQ device. For example, to understand correlated quantum many-body problems. And then I introduce the quantum algorithm. That's since we cannot do anything on quantum computer currently. So in this area, the main paradigm of quantum computing is so-called quantum classical hyperzed paradigm. And the central part is this quantum classical loop. That is, we can imagine that you have some recipe that can guide the quantum computer to generate some quantum state, and then you can measure this state to extract some information, and then you send this classical information to the classical computer and perform some calculation, and then you can generate a new recipe to guide the quantum computer to generate a new quantum state and form this quantum classical loop. And so based on this quantum classical hybridized paradigm, the main algorithm in the Nisco area is called the rational quantum algorithm, and it composed by 3 parts. And the first one is the objective function, which contains the parameters which related to quantum circuit. It's actually the recipe I mentioned before. And the goal is to minimize this objective function. For example, the total energy of the system can be considered as objective function. And then the central part is parameterize the quantum circuit, which can take the parameters in objective function, and it will be performed on a quantum computer. For example, some wave function answers to describe ground state. And also, we need the help from classical computers. That's the classical optimization step. And we have some classical optimizer for updating the parameters in the quantum circuit. And based on the values of the objective function evaluated on quantum computer, also other functions related to the objective function, for example, that the derivatives of the objective function, which also evaluated on quantum computer. And this optimizer is performed on classical computer. For example, you can use some gradient descent optimizer as an example. And to specialize to solve quantum many-body problem, which we have interest, is the algorithm is called the rational quantum eigenserver. It's a rational quantum algorithm for finding the ground state of a quantum many-body system. Here we consider the Schrödinger equation that our objective function is the energy of the system, and our parameterized quantum circuit is parameterized unsaturated state. It's a rational wave function, and it can be realized on quantum computer. Since it can be realized, you can measure the energy and also the derivatives of energy, and send this information to some classical optimizer on classical computer, and update your parameters in the parameterized quantum circuit, and to get a new ansatz. And with several iterations, finally, we hope that this ansatz state has been optimized to close to the ground state of this Hamiltonian. So this VQE give a path to achieve useful quantum advantage. Here, finding the ground state of the quantum many-body system on Nisco devices. And why the VQE is very important currently, that's because if you can achieve a scalable VQE, which means scalable scale up to 500 to 1,000 qubits, you can roughly say that you can solve a small group of quantum many-body problems, and is equivalent to achieve some useful quantum advantage in the near term. But there are still a lot of issues related to the VQE algorithm. for the parameterize the circuit uncharged part, we need to track if the uncharged is scalable or not on Nisco device, or if the uncharged is has the enough expressibility to express the ground state. And even your uncharged has these 2 points, but for instance, if your uncharged have too much parameters which cannot be optimized, that's your uncharged is still useless. Also, for the classical optimization, that you need to track if your optimizer has the ability to get the global minimal, and also you need to care about that. If your classical optimizer is efficiency for the Nisco device, since currently the quantum resources is still very expensive. And also you need to consider some suitable problems. For example, that your problem should in lower spatial dimension, for example, 1 dimension and 2 dimension. Also, it's better to consider some simple example like spins, like Hashimura model. And then I will show some examples from our group. Yeah, the first example is use VQE to simulate gapless fermions. So although we know that we cannot achieve quantum adiabatic process currently, but we can borrow the idea of quantum adiabatic process to design your uncharged. So here you can consider each of the small time period as a discretized time evolution operator, and in each of the time period, you will have this small time evolution operator. And previously, in the quantum adiabatic process, this time period is fixed by some scheduling function. But here, you can free this time period as some parameters, and then you can construct some uncharged function, some uncharged state, which called the discretized quantum adiabatic process uncharged, DQAP uncharged, also called QAOA, which means here your quantum adiabatic evolution path itself is to be optimized. And here shows a figure that to show that the QAP optimization process. After the optimization, your DQAP uncharged should provide some similar path like the quantum adiabatic process. And finally, your final state should be close to the solution of the state. And one of the central question in this for this uncharged is that how many depths, I mean, how many time steps you need to represent the exact ground state. And so here we consider the most simplest example. That's one-dimensional free fermions and it's spinless fermions. And we use the procedure I mentioned before to construct the DQAP uncharged. And the number of parameters in this uncharged is equals to doubled the depth. And so we found that no matter the system size is, the exact ground state can always achieved after the depth increase to system size over 4. So we need to understand that this magic number R over 4. So and then we found that this R over 4 is actually related to the causality cone that related to the information processing in the system. After the depth increase to R over 4, that's the left end and the right end qubits can be connected by the circuit, which means your information can processing in the whole system, and after that, this answer can give you the exact result. Okay, and the second example is the simulation of a 3.5 Heisenberg model. So here is the Heisenberg model, and we can rewrite it to swap operators. And again, we can separate this Hamiltonian with odd bound and even bound, and call the construction of DQAP ansatz, and then you will form your DQAP ansatz, which starting from the ground state of the H1. H1 here is just the Heisenberg model with only odd bound, and in each of the time period, you can see that each of the element gate is the exponential of swap operator, and so we can call this circuit E-swap circuit ansatz, and physically that this E-swap circuit ansatz actually form something called a resonating valence bound RAB state, and we know that in the study of the quantum magnets, that the RAB state is a very important ansatz wave function. It can represent any spin state like magnetic order to electric order, and also valence bound solid state. So we found that this DQAP ansatz actually construct such a RAB state, since you can see that you're studying some from dimer covering bound, that the direct product state of your bound, and then you apply a lot of E-swap gate, and this E-swap gate will change the bound pattern, and finally it will form some type of superposition of this bound covering, and it is nothing else but a RAB state, and so we can realize this circuit ansatz on real device, and just for very small system. And we notice that use this E-swap circuit, we can actually achieve the exact energy within the statistical error. And in comparison, that in previous study that people study the same system on real device use the other type of circuits, but they cannot achieve the exact ground state. So which means that our RAB type circuit ansatz actually catch the physics of the Heisenberg model, so we can achieve the exact energy. And then we can actually go one step further, that we know that if you consider a periodic boundary condition, that your wave function should be translational invariant, but the E-swap circuit somehow break this translational symmetry, but you can restore it by applying some the projection operator. Unfortunately, that the projection operator itself is not a unitary operator, so it cannot be directly realized on quantum computer, but you can consider it as some linear combination of the unitary operator is possible, and then finally your energy expectation value has this form, and you can evaluate each of the term individually on the quantum computer, and then sum over them on classical computer. And you will see that in a much larger system, after you consider this projector procedure, use very shallow circuit, you can actually achieve the exact ground state, which means restore the physics on quantum computer is very important. Time is up. Oh, sorry. So the final application is actually I already showed that in my poster session. That so maybe we can skip. And so here we can we just here we also construct some very physical circuit ansatz that can achieve the exact ground state for some non-exact showable correlated magnets model. And so in summary, that quantum computing provides a new way to study the correlated quantum many-body system. That's the quantum simulation. But currently we are in niche area. So the main approach is noisy quantum device plus classical hyperledger algorithm. And for the study of quantum many-body system, that's the VQE. And we try to use VQE plus current noise devices to apply them to the study of correlated quantum many-body systems. Okay, thanks for your attention.